Hello, good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. So the SETI Live is a discussion between scientists that we have every week here at the SETI Institute, and we talk about astrobiology, astronomy in general, and today we are going to talk about a very interesting mission dedicated to planetary defense. So to have this conversation, I invited a scientist involved in this mission called DART, scientist named Andy Rifkin. Hi, Andy. I'm waiting for you to drink to say hi to you. It's perfect timing again. How are you?
Of course. I'm good, Frank. How are you? It's nice to see you.
It's good to see you. After seeing each other or talking to each other on Twitter only, I'm glad to finally see you in person, in animated,
That's right.
basically.
That's right.
So, Andy, you are a researcher at Johns Hopkins University and APL, right?
Yes, I am.
And you're also a scientist at the involved in the DART mission. So that's the topic of this conversation. So I remind our viewers, wherever they are on this planet, that they can tell us where they are watching us from, tell us the place, the location, the city, where they are located physically. And also we will take some questions from you. So listen to Andy, and if you have questions, you want some clarification, we will take the time to answer to your questions, okay? So Andy, let's talk about this DART. What is DART, first of all?
Sure, so I have a few slides, if appropriate. Awesome, so let me just kind of share the screen here. Now that we've got over a year of practice sharing screens. So DART is part of Planetary Defense. Planetary Defense is, of course, our efforts as a species to try to make sure that we don't get done in the way that dinosaurs and other species have, and that if an asteroid or a comet were to be on a collision course with Earth, that we would know about it and be able to do something about it. So this little graphic over here on the right shows the different techniques that we think we might use if we discovered something incoming right now. The one at the bottom, if we find something that's small enough that isn't going to do a whole lot of damage to the Earth, then it would just be a matter of warning people of the time and place, tell people, hey, stay away from your windows, maybe go into your basement, wait until the shock wave, and then you can come out. That's the sort of thing we might say if we knew an impactor maybe the size of the thing that hit the Ukraine several years ago. That would be the approach we would take. For something that's very large or something that we don't have a whole lot of warning time about, or both, the most powerful tool we have is a nuclear device. But as you might imagine, there are a lot of reasons we don't want to go to use nuclear devices to deflect asteroids. We certainly can't test them because of international law and some other things. So the option that has been developed that's kind of in between is something called a kinetic impactor. Kinetic impactor is basically you take your spacecraft and you ram it into the threatening asteroid and you change its orbit that way. So the mission that we have developed to do this is called the Double Asteroid Redirection Test, or DART. We launch this fall. We carry a CubeSat that the Italian Space Agency is building, and we are going to impact the moon of an asteroid system. The main body is called Didymos. The moon is called Dimorphos. We come in at something like 6.5 kilometers a second. So that's fast enough that you could travel from New York to Honolulu in 20 minutes or so. So coming in very fast. And then after we impact, the results of what we did will be measured by observatories on Earth. We'll get a little bit of data from the CubeSat as well, as it kind of passes by a few minutes after the main spacecraft does and takes images. Just to kind of show the scale of the things we're talking about here, Dimorphos, which is the body we're going to impact, is kind of similar in size to one of the Great Pyramids in Egypt. Our spacecraft is the main part of the spacecraft, not counting the solar panels, is kind of the size of a vending machine. And then when you add the solar panels, each solar panel is maybe the length of a bus or so, going out on either side.
This mission consists basically into testing a technology, kinetic impactor, onto the moon of an NEA asteroid, and the spacecraft itself will impact the moon, but before impacting, it will release this tiny CubeSat, which is made by the Italian Space Agency.
That's right. So we release it. The exact timing is still a little bit up in the air, but the CubeSat is about the size of a cereal box. It carries 2 cameras, so it will make its close pass to Dimorphos a few minutes after DART impacts. It will image the plume of debris that's made by the DART impact, and then after it passes by, it'll turn around and take pictures of the far side of Dimorphos, the side that DART doesn't get to see because it's on a one-way trip, and return that data to Earth. And then all of those data, the pictures that DART will itself take on the way in, gets returned to Earth, and then measurements from telescopes on the Earth will determine how much we changed the orbit of the asteroid moon. And again, you do all the math. We say we know how heavy our spacecraft was. We know how fast we hit. So we know the momentum we brought to the moon. So then the question would be, how much of that momentum, or how much did we change the momentum of the moon, given the momentum that we brought in?
Wow, that's a very impressive mission. But before we talk more about it, I just would like to say that we have a lot of people interested in planetary defense on this planet. We have people from Puerto Rico, Portugal, Ghana, Eureka, Illinois, Mahwah, New Jersey, Germany, Sweden, Norway, San Jose, California, Wichita in UK, Poznan in Poland, Wales, Kalamazoo in Michigan, Colorado, Valdivia in Chile, Halifax and Surrey, England. A lot of people from everywhere in the world. So welcome.
That's great.
That's great, because planetary defense is universal. It's protecting the planet, and everybody needs to know about planetary defense and need to know about this fantastic program we do in planetary defense.
That's right, and I'll do a shout out.
Go ahead.
Sorry, Frank. I'll do a shout out to Mahwah, New Jersey, because I grew up just across the border, and I've got cousins in Bergen County there. So, hello to Mahwah.
Very good. So you mentioned that it's a space mission. True, we will go over there, impact, so dive as a space mission. But then the scientific information will be collected from the ground, most of it, in fact. Can you tell us a bit more what's gonna be the follow-up on the ground from ground-based telescopes? What exactly astronomers like you, I think you're involved in that, are going to do specifically in September 2022 or something like that?
Absolutely. Yeah, it's a great point. It's interesting that compared to most space missions, a lot of the really important data gets collected after the spacecraft is gone. So the Dimorphos and Didymos together are as I showed, they're small, they're very close together. They're less than a kilometer separates them, so it's the size of like an airport, a typical big city airport, between them. And so we are never going to see them from Earth as more than one point of light in telescopes. Goldstone radar will see it as 2. Arecibo would have, but of course, unfortunately, we don't have Arecibo. But for most of the telescopes, it's just going to be a point of light. What we'll do is watch that point of light and watch the brightness of that point of light change. And as I guess I do have another slide I could show maybe, but as the moon goes around the main body, when it comes in front, it partially blocks the light from the main body. And then when it goes behind, it is blocked in turn. And these are called mutual events. There was an eclipse yesterday, or an eclipse this morning, I guess. An eclipse is basically a mutual event. So we'll be watching Dimorphos eclipse Didymos and vice versa. We've been watching them do that for years, so we know the timing very precisely of how often that happens. And then once we impact the moon, we're going to keep watching, and that frequency is going to change. Right now, it happens every, twice every 11.9 hours. It moves in front, it moves in back. We think that'll change by something like 10 minutes. And we'll be able to measure that. And again, that's how we will know how much we changed the speed and how much of the momentum we gave to the moon.
Yeah, so that's a technique that we use to discover, in fact, binary asteroids, observing mutual events, those variation of light due to primary, secondary. You knew I would have some material with me, right?
Of course.
So the moon orbits around the primary, and if you're located in the right line of sight, you will basically see that the moon is the brightness will drop because you not see the moon anymore, basically. It's behind or in front or behind. So when we look at the light curves, we basically see this drop regularly, and that's the timing of the transit. And so what you expect to see after this impact is the moon's being slightly accelerated or retarded or slow down. So you will see a slight shift of this event. And from that, you get information about the mass of the system, etc., the density, but also the dynamic effect. It's kind of a new physics, in fact, too, when I think about it. Like impacting an object into an asteroid is not something we have done. We have impacted on the moon. We've impacted something on a comet, but on a rocky asteroids, that's not something we have done a lot. Can you give us an overview about what we know so far?
Yeah, absolutely. Just to back up slightly, like you said, the light curves and measuring light curves and measuring mutual events is really important in astronomy. We did it, like you said, we've discovered a lot of binary asteroids that way. It's the same thing also that is used to discover exoplanets. So it's when the planet moves in front of the star, you see a change in the light you get from the star. So it's a fundamental, really important technique in astronomy. In terms of impacting bodies, the first missions to the moon that landed on the moon were hard landings. They were sent straight in, and of course those didn't move the moon. The spacecraft were too small, the moon's too big. The deep impact mission impacted a comet, again, as you said, Frank, but that was designed to kind of dig up subsurface material. Again, it didn't move the comet. The impactor was way too small. The comet was way too big. There have been, again, some small impacts on asteroids. Hayabusa 2 last year, I suppose, maybe it was the year before, sent a small impactor to impact the surface of Ryugu. Again, that was designed to dig up material. It was not designed to move Ryugu. They were surprised because the crater was much bigger than they were expecting. So the big change that we're doing, or the big difference in the expectation, is we do want to move Dimorphos. This is the first time that we are trying to change the orbit of a celestial body. So these other results from deep impact from Ryugu are very important. What OSIRIS-REx did when it came in to take its sample, it wasn't an impact, but it did come down, interact with the surface. And so all of these things are gonna help us understand what are put together, are gonna help tell the whole story. But yeah, we are doing something. We're coming in a lot more massive and a lot faster. So we expect it to be a whole different ball game.
Yeah, it's a very important part of the mission. It's the first time we are going to try to move an object in space outside this orbit, not a man-made object, a human-made object, a natural object. That's going to be an interesting result. And I do remember for Temple 1, we had some surprises, right? The crater was much brighter than expected. I mean, we basically saturated the detector. So we're probably going to have surprises for this one as well.
Yeah. It's also interesting because we're in a binary system. Mm-hmm. And so the dynamicists on the team are very interested because it's not as simple as you have an asteroid, a material that's moving faster than the escape speed is going to go, and material that's moving slower is going to stay. There's the escape speed from Dimorphos itself, but then there's the escape speed from the system. And so some material might escape Dimorphos, but stay in that system for a little while. We are studying now, trying to figure out how much material how much debris we're going to throw off, how much ejecta we're going to throw off. We have our fingers crossed that that there'll be something detectable from telescopes on Earth. But we
big fragments.
We certainly can't promise. Yeah, we don't. We certainly don't know yet. But
so I heard
it would be.
I heard there is some researchers who are trying to predict that by doing experiment, by breaking rocks, basically, right? I'm making fun of them. They don't break rocks. They impact high velocity bolids into meteorites to kind of see what the effect of this impact, to predict what the effect of the impact will be. So there is people working on that at the moment.
Oh yeah. And there are, I think one of the big unknowns is the surface texture for Dimorphos. So if it's something like a beach, if it's if the mineral grains are like sand size, and if the material is not very dense, then we think a lot of the impact energy will go into kind of crushing material and not necessarily throwing a lot of ejecta off. If it were to be one big rock, we don't think it's going to be one big rock, but if it were to be one big rock, then we would make a lot of very fast debris, and that would potentially push, give us a much bigger push than we would have had otherwise. And sort of there's this area in the middle, we like I said, the spacecraft is about the size of a vending machine. If the surface of Dimorphos is covered with blocks that are the same size, or we happen to hit a block that's about the same size, it might end up looking a lot more like the whole thing is rock instead of the whole thing being sand. Mm-hmm. So we're excited. We're really kind of not sure what we're going to find, but we've got we're going to be taking images. This is we talked about the lunar missions, the Ranger missions that just took images all the way in until they crashed. We're going to do the same thing. We're going to take images all the way in until we can't anymore. So we do hope to have at least a few that have really, really high spatial resolution.
Yeah. You're going to basically see where the impact is happening by looking at the structure on the surface. All right. So we have a lot of questions, and we have people joining us from La Porte, Indiana, New York, Glasgow, more people from Indiana. And we also have some donations. So thank you very much, Sabine, for the stars. And we also have a donation from Tim. Thank you very much for supporting the SETI Institute. So one thing I wanted to mention, to discuss with you, is this famous mission called Hera, or Hera, depending on where you're from. So what is this mission?
Excuse me, I had to sneeze there. I missed. Yeah, thank you. You said Hera, and then you asked a question, and at the very end.
Yeah, can you tell us a bit what is Hera? What's going to be this mission?
Absolutely. So when DART is not the first time that people thought about impacting an asteroid to try to move it. The first idea actually came from Europeans. And the European Space Agency did a study, probably something like 20 years ago, called Don Quixote, and in which there would be a spacecraft that was monitoring, that would show up at an asteroid, which is just a single asteroid, and would monitor the system, would characterize the system, and then another spacecraft would come in, hit it, and then the spacecraft sitting there would document what happened. So it turned out that having two spacecraft was too expensive for what ESA was hoping to do at the time. When we started to work on DART, we had been working closely with a group of Europeans who were very interested in seeing if ESA could provide an observer spacecraft. It didn't turn out to be the right time for that, but they were able to keep working and come up with the Hera mission. So the Hera mission will launch, I think it's in 2024, and I believe it shows up at Didymos in 2026. My apologies if I'm off. I might be off by 2 years.
It's okay.
Yeah, and it will basically see in detail what it is that DART did. So it's going to carry a lot more instruments. DART is only carrying one camera. That's all we have, and the CubeSat, of course, LICA Cube. Hera will carry more instruments. It will carry 2 CubeSats of its own. I believe it has a landed element. It will do, characterize the crater that DART made. It will be able to make a very good estimate of the mass of Dimorphos. So putting the 2 missions together, we're really gonna each one works great in tandem with the other. We have a lot of colleagues on that team. A lot of them are working with us now, and in some ways, we're gonna pass the baton to them in 2023 when our mission ends, and they'll continue the great work.
So to summarize, DART is going to impact, and then Hera is going to look what the result of this impact has been in detail, basically probably seeing some pristine element, not pristine, but at least maybe a cloud of dust around the primary, or some fragments, or some result of this impact.
Yeah, it'll definitely be interesting. Again, the dynamicists are interested. We were going to have a few years in between. I don't know what material might have cleared out of the system and what might still be in orbit. And certainly from not Planetary Defense, but Planetary Science, there'll be a very fresh crater that they'll be able to look at and see how, what very rapid processes might happen or take longer, because it's just going to be a 2 or 3 year old crater.
Nice. So we have a lot of questions. I'm not going to go through all of them, but one of them is about the DART mission itself. There is rumor that the DART mission will fly by an asteroid called 2001 CB21. Is that true? And what kind of information will we get?
It is not true. There was one point early on in the mission when we were hoping to do a flyby, but as timelines changed, our launch date changed, among other things. It was decided that the most important thing is for us to get to Didymos or to Dimorphos, I guess. So when push came to shove, when the decisions got made, that was decided we're just going to go straight there without any detours.
Okay. Yeah, the primary mission is to go to Didymos, so let's focus on that. And it's true that the time changed for the launch, so then the star needs to align, but in this case, the asteroids need to align to be able to visit multiple of them. Another question I got is what's going to be, could you see the event with the Hubble Space Telescope? Is there any plan to do this? And I will add, is there any plans to do the same with the James Webb Space Telescope?
Yeah, it's a great question. We have plans to look with James Webb, actually. Dr. Christina Thomas is the leader of the observations working group for the mission for DART. And she and I have time with James Webb. The trick is that James Webb is designed to look at things that are moving slower in the sky than Didymos is. So it's going to be a tricky observation. We think what we're going to have to do is kind of set up at the time we want, and then it'll kind of make its way across the field, and we'll have James, the telescope move as fast as it can to hold on to it for as long as we can. But we are planning to make those observations and then some other ones later on when Didymos is moving more slowly. We're going to propose for Hubble time, but that is a proposal. We have to write a good proposal and convince the reviewers that it's worth doing. So hopefully we have a good case to be made.
Yes, it's
and those might be those might be double anonymous. So maybe we're not gonna. I can't say because the proposers is supposed to be anonymous, so I don't know what's going on with Hubble. I should say that.
Okay, let's see. We have people joining us still from Kent, from Norway, Hamar in Norway, Ontario, Canada, Mexico, Boston. Welcome. We are taking a few more questions here. Oh, someone asked, why don't we try to capture an asteroid? Why do we try to destroy it, maybe, or to push it away? Could we try to capture it? Is there any study to do this kind of work?
So, I'll take a nuance there. We are trying to push them. We're not trying to destroy them. Usually, if you watch the movies, they try to blow it into a zillion pieces, and that's not the strategy that we have, because in at least one of those movies, you just break it into 2 or 3 pieces, and one of them still hits. So we don't want to do that. We want to keep them intact, and just push them away. In order to capture one, that would take a lot of energy and a lot of it would take a lot of energy, and it would be very expensive. If you think about how expensive it is to send a rocket to the moon, or a rocket to Venus, or choose your favorite planet, and those rockets are very, very tiny compared to even a small asteroid. So it's capturing an asteroid would be kind of doing that in reverse. You'd be saying, I'm going to take this thing that's hugely massive, and putting a rocket on it to try to move it to Earth. Imagine trying to take a piece of rock, or a ball of gravel that's 1 kilometer across, and how much energy it would take to move that into the asteroid belt. It's the same thing in reverse, just too prohibitive.
Right. Yeah, so I have one final question for you, in fact. So this month of June is Asteroid Month. What Andy Rifkin does for Asteroid Month? What do you do? What's your main activity for Asteroid Month? Anything special?
Every month is Asteroid Month for me, Frank. I think it's great that there is this time for people to think about asteroids a lot. I try to be a bit of an asteroid person on Twitter. Oh, you can follow me on Twitter, I guess, maybe. So I talk about asteroids there. But this coming week we have the DART investigation team meeting. So that's not timed for Asteroid Month, but it does happen to fall during that. So I try to support people as they talk about asteroids and stuff. But like I said, every month is Asteroid Month.
It's your job after all, right? You're not gonna make a song about asteroids? I know you're a musician.
I could. No, it's true. It's true. I haven't done an Asteroid Month one specifically. I do have a DART song. I do have a few others, and if you look on YouTube and you search on my name and DART song, you'll run across it.
So if you follow Andy on Rifkin, and if you don't know, his Twitter handle is ASRifkin, you can also write to him and ask him to make a song about asteroids. That would be great. And if more than 100 people do it, I think you will do this. You will prepare this song and singing live in front of the audience, right?
Live? Oh, I don't know about live. There's live in front of everybody. You got everybody together. But I could see what I could do. Yeah, I can see what I can do.
Okay. Yeah, because that's just the reason I'm just mentioning this is because, as astronomers, we're not only boring people who spend their time in telescopes or in front of computers writing grants. We also have a life. And Andy is one of these astronomers that I like meeting at conferences because always a great story to tell, and always has some fun ideas. So thank you,
Thank you, Frank.
Thank you, everybody, for following us in the SETI Live. Thank you for supporting the SETI Institute as well. Remember that you can just support us by following us on social media or simply by liking this video, writing comments about it. We take the time to read your comments. So if you have any questions, take the time to write them. I will spend my time answering to some of them and ask Andy to help me in case. So support us also by, you can make a donation. Thank you again to Tim and Sabine for this donation as to be received today. Very appreciated. And also by sharing those videos. I mean, that's very important that you share the love for space. So sharing this video is one way to do that. So if you like what you hear, if you think it's cool, it's interesting, send it to your friends, to your family and say, hey, look, there was these two astronomers who talk about planetary defense. And that's a fun topic of discussion in any case. So thank you very much again, Andy. Very great to see you in person. ECU.
Yeah.
I hope to see you at the AGU in New Orleans in December.
Oh, New Orleans. I love New Orleans. I love New Orleans. I don't know. We'll try.
All right. Well, thank you again. And thank you to all our viewers. Bye-bye.